Looking at this graph, um, we may be interested in the highest value of a function. The first two functions are functions of one variable, and the two seconds are the graphs of function of two variables. So when we think about the maximum or minimum, usually we look for the highest value. So if we look for in the first graph, we see that we don't have a highest value because the function takes large values. In the second also, we don't have a maximum. Also for the minimum here, yes, we see that 0 is at -2 and 2 is the lowest value of our function. But for the second function, we don't have smallest value, since my function takes large negative values indefinitely. So, but still there's points, these points level y equal 4 is important. This level y equal -1 of the function is important because it gives us new information. It remains the largest value over an interval of our function. Here also it remains the largest value over an interval of. So we need to distinguish there's two distinct extreme points. Similarly, this is what we see also for function of several two variables. We have the small mountains that seems that values are giving information on the behavior of the function. Here also, but globally maybe we don't have the largest value or the smallest value. Okay, so this is why we need to distinguish first the definition, what we mean by extreme points. Okay, so we will say that point x0 is so we will call a local maximum point, local maximum, or respectively minimum point. If we can compare the values, still we have the same comparison for the meaning of maximum. So we need to have fx greater or equal to fx0. Okay, so respectively for minimum we should have fx so remain now this is fx0, this is minimum, so I did mistake here, so let's correct it here. So it will be fx remain less than fx0 is the largest value, but locally fx is greater than fx0, so fx0 remains the smallest value locally. Locally means for any x belonging to a small ball. This is what we mean locally. It's enough to find a small r, even it's very small, it's enough. Okay, so this is, and we need to distinguish what we mean by global. So x0 is a global maximum point, respectively minimum points. If we have this time of the comparison holds for any everywhere in the domain are considered. Okay, fx greater than fx0. Okay, for any x in the domain of the domain we are considering, okay, the optimization problem. So this is, yes, we need to make this clearly this difference. So and our purpose now, so how can we find those points? Those points, we know that they are important. How we can find them? Okay, how we can, given a formula for our function, how can I locate this points for candidate for optimality? Okay, so there is a theorem. We did it for function of one variable. If you remember, there is Fermat's theorem saying that if we have a local extreme point, then it will be a critical point, if you remember. So this result is extended to a function of several variables. So here is the main theorem then. Okay, so the theorem, let's put it here. Here is my theorem. It says that if f is differentiable, f is differentiable, okay, is differentiable around, okay, on is differentiable function, okay, on small interval, a small ball centered at x0, okay, and if x0 is a local extreme point, a local extreme point. So when we say extreme point, means either a local maximum or local minimum. Then necessarily, so we need differentiability, then necessarily it will satisfy at this point the gradient equals 0. Okay, so this is the main theorem. The theorem says that if I'm looking, so it doesn't say the solution of the gradient are necessarily extreme points. Okay, so let's put this as a remark, important remark. So the theorem, so the solutions of the equation gradient f x0, okay, equals 0, are candidates only, are candidates for optimality, candidates for optimality. It's not necessarily, and the classical example we give, if you remember, we can see it with the real function of one variable example. Okay, example fx equal x3. Remember, you have f prime x equal 3x2, so it is equal 0. F prime at 0 equals 0. Still we have but 0 is not a local extreme point. Extreme point. So how we justify for any r positive, okay, we have fx, that is x3, is greater than 0, which is f0, but this is true for x or for any r, or yes, r, so that I speak locally, okay, so up to r, and fx, which is always x3, remains negative, which is the values remain less than the value of 0 for x belonging to minus r0. So if you to explain this, so here is my curve, my function does like that, okay, y equal x3. So the theorem says here, what I'm explaining here, the point 0, 0 cannot be a local extreme point, because locally we should have this, the comparison over a small ball, which is small interval centered at the point 0. But here it cannot happen, because we have always this change of behavior of f. F remain positive, remain above 0 from to the right, and below 0 to the left. Okay, this is my r, this is my r. Okay, I'll say. So for any r positive, we show this. Okay, so 0 cannot be a local extreme point. Even we have it is solution of the derivative equals 0. Okay, so the theorem allows us just to restrict our search domain search, reduce the domain of search. Instead of working in the whole domain of f, we are reduced to uh, so to find solution of this equation. Okay. The second remark is that if the candidate R solution equation like that, gradient f equal 0 is nonlinear. Is okay. Is a nonlinear equation, vectorial equation. So it's not easy always, not easy to solve. Okay, so often we have to use approximate methods. Okay, for our study, of course, we want to develop all the basic theoretical theorems for the optimization domain, and we need to solve them. We will deal with feasible examples, so that we apply all the theorems. Okay. The theorem doesn't say once we have the candidates, is it maximum or a minimum also. Okay, so this is another step. We will see it next time to identify the nature of the response. Okay. Okay. Yes. So in this theorem, we used the assumption. We used this assumption of differentiability. Okay. We can have. This is another remark. We can have. We may have. Okay. We may have extreme point. Extreme point without the assumption of differentiability, without differentiability. So let's without differentiability assumption. Okay. Okay. For example, a classical example also here. We have the example of y equal absolute value of x. So we have the following graph, if you remember. So my function at 0 is not differentiable. Okay, so because remember, differentiability f prime at 0 would be the limit of fx minus f0 if it exists. Okay, but if you write this limit, its absolute value of 0 is 0 over x, but this limit doesn't exist. Okay, because you will have a limit to the right, which gives you x over x limit of 1, which is 1 as x approaches 0 plus, and you will get a limit at the left, which is minus 1. So the limit doesn't exist. We don't have differentiability, but we have f0, which is absolute value of 0, which is 0, always less than or equal absolute value of my function. So for any x in the domain, so it's 0, which is f0, is the minimum, the global minimum of my function over the whole domain, and it's also a local. Okay, so here also we have an important remark. If our domain, if we are working on the domain, the whole domain, if S is open, and x0 is a global extreme point, then it is a local one. It is a local point. Okay. It's like here, R is it is open, 0 is a local, is global minimum. It's also because the comparison is done over the domain, so it remains it remains true by restricting the domain to an interval low centered at the point considered. So these are the main properties. Yes. So let's give these points. This point we called it for the 0 for the curve y equal x3. Remember, we called it an inflection point. Okay, there is here this behavior. We can see it here also for function of two variables. For example, we see the points on this line. They cannot be local maximum or local minimum, because any ball, small disk centered at any point here, we see that there are values of f that are above the value 0 and below the 0. So even we can concentrate on 0 here. So such points are called saddle points. Okay, so let's give the definition of saddle point. Point is saddle point if we have a saddle point if we have the function remains takes values above, okay, a saddle point. So f differentiable, so let's f differentiable has a saddle point at x0 if if for any r positive, okay, f takes okay, for any r positive f, so f takes values takes values fx greater than fx0 and values fx less than fx0 for these for x on this ball. Okay, it changes. Okay, so we need that. We need also the definition of critical points. The other definition is critical points. We will call as for function of one variable. The x0 is critical point. X0 is a critical point of f if we have f prime at x0, which is gradient here, equals 0, or f is not differentiable, okay, at x0. So that we regroup all the candidates for optimality. So when we have a function, we are looking for the local extreme point. So either f is differentiable, then necessarily it is solution of gradient f equals 0, or f is not differentiable, so we gather all the points where f is not differentiable. Okay, so this is what we need. Of course, there are other theorems there where we have less regularity. Okay, not necessarily for at an interior point. Here we are working with an interior point, so there are other theorems, but you can read on them, okay, to have an idea how it works. Okay, so this is mainly what you need to know about this content. Okay, so today we saw critical points are the necessary condition, okay, necessary condition for necessary conditions for optimality, okay, necessary conditions.